Thank you for joining our third webinar in our four-part Open-NFP Fall Webinar Series. Today, David Hancock is going to present software techniques for programmable data plane virtualization. A copy of the presentation, archive replay, as well as any project code will be made available shortly after the webinar. These, as well as our previous webinars, can all be found on the classroom page on the OpenNFP.org website. David Hancock is a Cyberspace Operations Officer in the U.S. Air Force with experience in the Department of Computer Science, U.S. Air Force Academy, and previous assignments relating to cyber warfare. He received a master's degree from the Air Force Institute of Technology in 2011 with an emphasis on artificial intelligence applied to network security. Mr. Hancock earned a BS in Computer Engineering from Utah State University in 2004. Programmable data planes enabled by languages like P4 present intriguing possibilities for virtualization. Our virtualization solution for P4 devices allows them to simultaneously host multiple network functions for dynamic slices, compositions, and snapshots. We present applications as well as the tools and techniques supporting this exciting form of networking. Let me describe Open-NFP before I hand it over to David. Open-NFP's objective is to support and grow reusable applied research and technology development in data plane network functions processing. We do this by focusing on reducing the barriers to performing research in this space to researchers and developers creating, implementing, and verifying their ideas on production networking hardware. Open-NFP supports research in a wide range of technologies, including software-defined networking, OpenFlow, Open vSwitch, and P4. We support researchers with a variety of tools, including deeply discounted hardware, IDE software, and cloud access to development systems and direct support from our engineers and our research community. We also provide support in learning advanced networking concepts on our hardware through tutorials and seminars, such as the one we are performing today. We encourage proposals to research funding agencies. We invite you to join the 50+ universities and companies working directly with Open-NFP through projects. If you have any questions throughout, please submit them in the chat window. There will be a brief Q&A following the presentation. Thank you, and over to you, David.
Okay, so without further ado, I'm excited to talk to everybody today about my research, which is dealing with software techniques for programmable data plane virtualization. We're going to talk a little bit about why we think this is an important problem to tackle, our approach to the issue, and then I really think of this work in two phases. The stuff that we've been working on most recently concerns the controller, which provides a hypervisor for the control plane. Last year, we produced a paper in Connext. So for Connext 2016, we presented a data plane hypervisor, which is implemented as a P4 program that provides essentially predefined functionality at arbitrary points in the ingress pipeline. And by feeding it carefully constructed table rules, you can make it behave like any other P4 program that you like, and you can share. You can have several P4 programs actually inhabiting Hyperfor at the same time, and we'll talk about that in detail today as well. And then, time permitting, we'll get through a little bit of a demo and finally take your questions. Okay, so programmable data planes. We're talking about P4 environments. If you're not terribly familiar with these, this is where we now have software switches and hardware devices as well that we can deploy P4 programs to, so P4 programming language for defining the network functionality, and we can define our own protocols and protocol processing behaviors to our heart's content, and that's a pretty exciting new chapter in software-defined networking that is now including hardware devices as well as software devices. But we ask the question: how dynamic are these programmable data planes? Can we insert functionality on demand without disrupting important flows? So, as an example, think of a system administrator that may be re-imaging a lot of machines on his network, and these transactions consist of a lot of elephant flows, gigabytes of data flowing across the network to reimage these machines. And in the middle of all of this work, there is a security threat or some kind of requirement to reconfigure the functionality on the network somehow. Let's say that there's a new security threat that in order to mitigate this, we're going to want to deploy perhaps a firewall, an intrusion detection system, some sort of proxy, and it may have to be customized because this threat is something new that we've never seen before. And we want to be able to deploy this functionality without disrupting those precious elephant flows and disrupting all of the operations work that we want to get through day to day, right? And there can be any number of examples that kind of fall into that category of, on the one hand, you need to do operations, you need to do maintenance equally, and on the other hand, these contingencies arise that you would like to be able to change something about the network without disrupting those operations and maintenance activities. So this is an important problem to solve, even if you're just a single tenant and the only tenant that controls all of these network devices. But if you're in a multi-tenant environment, then it can perhaps be even a little bit more complicated. Can you change the functionality on a device that you're sharing with another tenant without disrupting what they're doing, so that we don't have to get together and coordinate downtime activity for everybody? That would just be unworkable, the more tenants that you get sharing the physical resources of this network. So we look to virtualization as an approach to solving this problem. We like virtualization for a couple of reasons. One of the properties that virtualization provides is isolation. So by pursuing virtualization on these programmable data planes and the control planes that interact with them, we can isolate tenants from each other that each get a slice of the network resources to use however they want. They don't have to worry about what's happening on the other slices or even be aware that there are other slices, ideally. And secondly, virtualization provides us the opportunity for some powerful abstractions. We can operate at a higher level, thinking about how we want perhaps multiple network functions to interact with each other, even on the same device. And we think about compositions. Can we compose these network functions together so that you have a service chain deployed to a physical device that you have access to? And can you do this dynamically so that you can have a truly modular approach to programming and configuring the network? And this modularity is as dynamic as anything else. Introspection is another possibility with virtualization. By taking a step back from the functionality that's running on that device, you can take a look and analyze what's going on and perhaps find opportunities to optimize or assist your troubleshooting requirements when things go wrong. Finally, maybe we think about providing standard functionality in a virtualization system that would just be a nice feature to have that maybe doesn't come natively with a P4 device, but if it's built into the programmable data plane hypervisor, then you just get that feature through software without having to do significant effort on your own part. Okay, so our approach, again, is through software, and I talked briefly already about the two aspects of this. The data plane hypervisor is a P4 program, and then the controller is a hypervisor for the control plane. In the controller, we have some functionality to discuss in terms of managing slices. So when I talk about a slice, I'm talking about the subset of physical resources that you're going to allocate to each tenant that is sharing that network. Simple example would be physical interfaces. So you might have a switch that has 20 interfaces, and you want to carve that up and say, tenant 1, you get 4 of the interfaces, tenant 2, you get 2 of them, and so forth and so on. And those physical interfaces then are part of the slice that belongs to that particular tenant, along with certain memory limitations. So you can give each tenant a bound in terms of how much memory they can use up for that physical device. And this is a simple way to define a slice. You could get more complicated. You could try to carve the device up in terms of flow space. So now we're talking about looking at fields in the packet itself and making decisions about what slice owns that packet, perhaps based on the IP address or some other aspect of the packet headers. Or maybe it's the state of the network itself. So there's a lot of different ways that you can define these slices. The implementations that we're talking about today, we're simply slicing the devices according to physical interfaces. But all of those other more complicated ways to do splicing are also possible. Slice management consists of a variety of tools that any tenant can log into the controller and make use of these tools. They can compile P4 functions for use on these Hyper-4 devices. The loader will take that compiled output and push that into the Hyper-4 instance. Rule interpretation is important because we want to write rules for the network functions that we wrote in P4, but those have to be interpreted now so that they make sense to Hyper-4 according to Hyper-4's tables, which we'll explain more about that in following slides. And finally, composition. Again, how do we combine various network functions together to provide some kind of a service chain to implement a complex policy on any particular packet passing through our device. Okay, here's big picture. There's a lot to unpack here, and we'll break it down over the following slides. But this is kind of a comprehensive view of Hyper-4 itself and what it's doing. Hyper-4 is, again, a P4 program that is compiled and pushed to a P4 device. It defines a lot of match action tables that provide generic functionality at arbitrary points in the ingress pipeline. And in order to make use of Hyper-4, we write functions in P4 that then get passed through our compiler, the output of which is a set of Hyper-4 table rules that will then give life to this Hyper-4 instance, defining its specific behavior that corresponds to what we've defined in that P4 function. And of course, we want to write rules for those functions, and those will need to get passed through a tool as well, the rule interpreter. Again, the output of that is a bunch of Hyper-4 table rules that then inhabit other tables within the Hyper-4 instance. And of course, we have a composer tool as well. And again, the output of that is also some table rules that get pushed to the instance of Hyper-4 to make it pass traffic from one network function to another, one virtualized function to another. Okay, and all of these tools are housed in the controller. And perhaps it'll make a little more sense if we step through it a little bit more slowly. If we look at a P4 device, in the beginning there was darkness. It was without form or function, but then along came somebody who wrote a function in P4 that defined a bunch of match action tables. There are no entries in these match action tables to begin with. Some of these tables might be simple things like forwarding, right? They might be looking at the IP address and deciding what port to send that packet out on. Okay, this traffic will come in through a parser that is defined by the P4 function. That parser determines how to break down the headers into various fields that we can address in that we can reference in the remainder of the pipeline. The deparser is implicitly defined, so basically it's just a reverse of whatever the parser is doing. Okay, I should mention, by the way, as we're talking about all of this, our work has been done in P4.14. There is a newer version of the P4 language, P4.16, but we're talking about P4.14 in case you're having questions about which P4 language specification we are referring to. Okay, along come the function table rules. So we decide specific IP addresses need to direct traffic to specific interfaces. We can write rules for that, and those get deployed to the match action tables. And that is your vanilla P4 operational concept. Instead, we deploy hyperfor.p4, and we then define functions that we pass through the compiler that produce rules for hyperfor. Then we can get a bit more flexibility. We can dynamically change things about these functions that perhaps we couldn't do before the P4 device was loaded with hyperfor. Okay. Previously, when you have function.p4, you want to change what's happening. Typically, in a P4 device, you might have to interrupt operations, take it down, and bring up the next function and proceed. There are certain implementations that are experimenting with more flexible arrangements, but hyperfor is really trying to extend that flexibility, that dynamic flexibility, as much as possible. Okay, and again, we'll want to write rules for those functions, pass those through the rule interpreter, and that produces table rules for hyperfor that will take care of the matches and the corresponding actions that we want to happen in response to those matches. And all of this housed in the controller. Okay, so one question that you might have is, how do we keep these functions separate from each other? We've not really talked about how maybe these are all inhabiting hyperfor simultaneously, but how do we keep those apart? What is the isolation mechanism? And this is the code that takes care of that. There is a metadata field called the virtual device ID. When I talk about a virtual device ID, that refers to that instance of a network function that's been virtualized and is now residing within hyperfor. So when a packet is received by hyperfor, one of the first things that happens after some initial parsing is it will take a look and see whether that virtual device ID field has a value or whether it's still 0. And if it's 0, then we're going to go ahead and apply this table in which we set the context for the packet. And there's simply just one action that can occur based on the ingress port that traffic was received over. We can set the context for the packet. So we set the virtual device ID, and we can set the virtual ingress port for whatever purpose we may need as the packet continues to be processed down the line. But that is essentially it. That virtual device ID will be part of the match fields for every table thereafter in the remainder of the hyperfor ingress pipeline. So any entry will have the virtual device ID specified along with it, identifying what functionality belongs to which virtual device or network function. All right, and that is essentially the functionality whereby we isolate those functions from each other. The controller presents a variety of possibilities depending on if you're the administrator or if you're a slice manager. We divide up those activities. Okay, an administrator may send a request that comes through the northbound API, and there are a variety of functions available to the administrator to do things like create slices, provision those slices, recognize physical devices that exist on the network, and part of that activity is identifying the addressing for that physical device so that we can talk to it over its control plane, okay, and so forth. Slice managers, on the other hand, want to do things with their slices to include instantiate applications. By application, I'm talking about a virtual device or a network function, and manage those, so populating the tables defined by those functions as necessary, and finally composing various virtual devices together. Okay, and so within the controller, we have a variety of roles that the controller needs to be able to support. Based on the role, there's a certain expected input, and we've listed here what the expected output is. As we've discussed before, for many of the transactions that a slice manager needs to conduct, the output is a set of Hyperfor ready rule transactions. And those will pass through the southbound API, where they get translated into the format that's appropriate for the physical device. So you may have a P4 device that's a software switch, like the behavioral model version 2 simple switch, which we've used extensively for our testing, or perhaps you have an Agilio card, and these each have distinct runtime APIs for managing the P4 objects that live on those devices. There is a working group in the P4 community right now for trying to standardize an API, so a standard P4 runtime, and in the future it'll just make sense to add that to the set of physical devices supported by the controller. But right now, this controller is architected to easily be extended to support different APIs as necessary, so we can manage these instances of Hyperfor no matter what P4 devices they're actually sitting on. Okay, within the controller, there's a lot of state to manage. We're tracking the slices, we're tracking the physical devices. A lease associates a slice with the device, so the lease is set up by the administrator when we provision a particular slice, and the lease will define what the memory constraints are, so it'll track how much memory is used up by the entries that a slice manager pushes to that physical device. And it will also define what the physical interface mappings are. And of course, we need to track the virtual devices, which can exist independently of physical devices. So we may need to create and even populate a virtual device before we're ready to deploy it to a physical device, and that's perfectly fine. So this just gives you an example of some of the commands available to the administrator for creating devices and slices and granting leases to associate those slices with those devices and define the constraints by which those slice managers must live. Some informational commands, and we can do some other, emergency activities. We need to reset devices or revoke leases or what have you. Slice manager obviously needs to be able to manage the slice through a number of functions that result in creating and destroying virtual devices. The interpret command will take a rule that is written according to the underlying virtual devices network function, and do the translation for the Hyperfor table entries that need to be produced. We can define a bunch of these rules in a file and do it all at once. We have a variety of methods available for inserting, appending, removing, replacing the virtual devices within the service chain associated with that lease. Okay, this interface has been changed a little bit to make a bit more sense just within the last couple of days, and hopefully we'll be able to get a look at that in the demo. Okay, Southbound API has been architected again to be able to accept, so we can define different subclasses of the device class, which implements various methods according to the P4 device's specifications. All right, for our compiler/interpreter, how does this actually work? The task is to take P4 programs and produce two different things. First off, we need to produce object code like Hyper4 rule sets. So these rule sets are going to be consisting of entries for Hyper4 tables that specify that program's functionality. We also need to produce, along with that, some guidance for the rule interpreter that will need to be invoked later when we actually need to write rules for those tables defined by those P4 programs. Okay, the compiler's job has to take a look at the various aspects of P4 programs. For example, metadata field addressing. Lots of P4 programs have a variety of metadata fields, and how do we refer to those within Hyper4? In Hyper4, we have one consolidated metadata field. It's in a metadata object called meta. The field specifically is data. It's one consolidated field because that allows us to refer to it quite easily by using ternary matching, for which we can apply bit masks and we can apply bit shifts as needed so that we can isolate the specific part of that one large metadata field that corresponds to the native function's metadata field. So the compiler has to be able to figure that out. There's a similar task with parsing. So when we parse a packet and we extract fields from that packet and map them to fields in the parsed representation for later reference in the remainder of the pipeline, we need to be able to handle that for Hyper4, and we take a similar approach that we did with metadata fields. We have one very wide metadata field that represents all of the parsed representation together, and again we apply bit masks and bit shifts as needed to isolate the specific part of that metadata field that corresponds to the native function's parsed representation field. You have to take care of matching, obviously, and the actions that are triggered by those matches. So sequences of primitives that we need to execute that comprise those complex actions. And finally, making sure that we take care of control flow. So there are ways in P4 whereby you can skip tables and jump to the next one if, depending on what particular action was invoked in the previous match. All right, so first off, when we need to convert a native P4 function into the representation appropriate for Hyper4, as far as parsing is concerned, here's an example of a parser that's defined for an ARP proxy. So it recognizes the Ethernet layer as well as the ARP header. And if the ARP is present, then it extracts that into the parse representation and then jumps into the ingress. Otherwise, if it's not there, it'll go straight to the ingress pipeline. And the results of the compiler will essentially be this flow that looks like this over here on the right. To explain this, you have to understand that in order for Hyper4 to have a programmable parser, we have deferred some of those decisions to the ingress pipeline of Hyper4. Okay, so there's a phase in the Hyper4 ingress pipeline that takes a look at any additional parsing activities that need to be done. So, for example, if we did not extract enough bytes from the packet based on the various table entries that are populating these Hyperfor tables, then we can issue a resubmit with the updated number of bytes that need to be parsed, and the packet will be resubmitted back to the Hyperfor parser. And this time, it'll take a look and see how many bytes need to be extracted and extract the appropriate amount. So, for example, when a packet is received by Hyperfor, by default, it will just extract 20 bytes. And then in the Hyperfor ingress pipeline, one of the first tables that it looks at after just figuring out what the virtual device ID is it will go to the parse control, which takes a look at whether this is the first pass or the second pass for the packet. The first pass, we need to take a look at the first few bytes of the packet, and we can supply a rule in here that says, hey, if we see this particular value in these specific bytes, then issue a resubmit, and this time needs you to take out 42 bytes, not just 20. And that will allow us to get not just the Ethernet header, but the ARP header as well. Okay, but if it's the second pass, or if that value is not found within the parse representation, then we'll just move along to the import parse representation table, which does the job of taking that parse representation and consolidating it into the single very wide metadata field that we discussed a minute ago. And based on what was actually extracted, we move on to the pipeline configuration table, where we can write to another metadata field that encodes what headers are valid or not. It's essentially a bitmap of possible headers that might be present in the packet based on the P4 function that has been virtualized. So in this case, a couple of possibilities. 1.1 if we have both Ethernet and ARP, 1.0 if only Ethernet but not ARP. Okay, and then we proceed to the rest of the ingress pipeline for Hyperfor, which is a series of stages for us to do the matching and actions. In order to carry out any particular match, we need to have the rule interpreter able to process any rules that we might write for the tables for our virtualized functions. Okay, so the rule interpreter has to consume information from several sources. There's a lot going on in this figure. We don't have to, get into the nitty-gritty detail, but up in the upper left, we're indicating that somebody has written a function called myfunction.p4, passed it into the controller where it's handled by the compiler, which produces a translation guide. And this basically will contain the mappings between tables and fields defined in myfunction.p4 and the corresponding values in hyperfor.p4. So those tables, those bit shifts and bit masks for specific fields and so forth. When we have a rule that needs to be interpreted, we write it according to how my function would expect it to be. That gets passed to the rule interpreter. And the rule interpreter will take that, it will take the translation guide for those mappings to the Hyperfor corresponding pieces. And it will take state for the virtual device as monitored by the controller. And all of these things together can produce the rule for Hyperfor that then gets pushed and implements that particular match and makes sure the correct action is then invoked. All right, we talked about this briefly before, but just to put it down in writing, we can do exact matching on arbitrary fields by using ternary matching, because when we do ternary matching, one of the nice things is that when you write a rule for a table with a ternary matched field, you include a bit mask along with that entry, and that bit mask can allow you to isolate only those bits that are relevant to the field that you're trying to match on. The way actions work is the result of a match in Hyper4 will invariably invoke an action in which we do a bit of setup. We're going to set a match ID. We're going to set a primitive code that basically instructs Hyper4 as to where to go next to carry out the behavior to execute the correct primitive. And so we're gonna set the metadata necessary to carry out that primitive. That will direct Hyper4 to invoke the correct table that's specific to that primitive, and whatever parameter types may be used by that primitive. For example, modify field has a variety of different field types that could be used as the destination and the source. So we'll have modified field primitives defined in Hyper4 that can be invoked as necessary to carry out the correct kind of modified field operation. Okay, that primitive gets executed, and then we go into an update state process, whereby we indicate what is the next primitive that needs to happen, and we do whatever setup necessary. And if there are any more primitives to do, then we just go back around in a loop. This has been optimized a bit in the current iteration of Hyper4. Last year, this would have been a more accurate representation, but we figured out that we can do this faster without having necessarily explicit state transitions, but rather encoding what needs to happen to make that action work at the very beginning of action execution. Instead of going to an update state every single time, we can just directly go to the next table, which will invoke the correct action corresponding with the next primitive in our native defined action. All right, and once this is done for a particular match, control flow then diverts to carry out the next match defined in the next stage. All right, there's a bit of substitution to do by the loader. The loader has to do some linking in order to convert the object code that is defined for Hyper4 into an actual rule that Hyper4 can consume. This is an example, a real example from an ARP proxy function that was put through the compiler. The object code was produced, and here we have the entry for setting setting up the pipeline configuration, as well as later on in the program. There's a point where we take a look where we actually modify the egress spec with the value of the ingress port. Okay, and there's obviously a whole lot more in the object code that I'm not showing, but as simple examples, we can look at this and we can kind of recognize that it looks sort of like a behavioral model version 2 API style command with a few differences. So we've got colons delimiting the different pieces of this. And then we have these fields that are in brackets that need to get replaced. Some of these fields, some of these tokens are in brackets because we don't know what those values are until that virtual device actually inhabits an instance of Hyper4. So the virtual device ID is the best example of that. And other tokens in brackets are there because perhaps it's more readable for me when I'm trying to debug the program. Here's an example of a value that is 0x80 with 9 bytes worth of zeros following after that. So we can just simply expand that by the loader, and the result. So we have similar things going on for each of these entries. But the result of the loader is that we get these finalized API commands, the table add instruction, for example, the expansion of that long value, the virtual device ID has now been correctly set up, and so forth. Okay, we're running a little bit short on time in order to get to the demo, but briefly, how Hyper4 supports composition. We have this virtual egress field, which is going to take on whatever values that the native program would normally be writing to the standard metadata egress spec. The compiler will substitute that for writes to this virtual egress field, and based on what that value is, we can decide whether we want to do some virtual forwarding. So virtual forwarding will result in that packet being sent back to the parser, but this time with the virtual device ID set up corresponding to the next virtual device in our chain. Okay, so there's a bit of work that's done at the end of the ingress pipeline, and there's a bit more work done in the egress pipeline where we take a look and see whether the virtual forwarding flag was set, and if so, based on that virtual egress value, we set the next virtual device ID, we set the virtual ingress port, and then recirculate that packet. The field list that is part of that recirculate operation will have all of the key fields necessary in order to make this work correctly. And with this composition support, we can support several composition abstractions. These are two possibilities. On the left, you could have a full-up virtual network within Hyper4. So we have several virtual devices defined, and conceptually speaking, they're all wired up to this virtual networking subsystem within Hyper4. Traffic comes in over a physical interface, it gets sent to whichever is the appropriate virtual device to start with, and then whenever that one is finished, it could potentially send the traffic on to any other virtual device that's connected here. And this is very flexible. It's also very complicated to implement and manage, but we opted for a simpler composition abstraction for now, which is the virtual device chain. So a simple service chain, so sequentially we can arrange these virtual devices together to apply complex policies to packets. Just one virtual device will take care of whatever it needs to do and then recirculate the packet so that it goes back around, and this time it will be processed by the second virtual device and so forth until it finally reaches the end, at which point the packet is sent out a physical interface. This is a virtual device chain in a little bit more detail based on the setup phase. When the packet is first received, we take the physical ingress and then map that to the virtual device ID, the virtual ingress. In the remainder of the pipeline, there are going to be a variety of activities that can affect the virtual egress. That virtual egress then gets mapped to the next virtual device ID in the chain. This is the behavior that applies to these first two virtual devices within this specific chain. But then, if it's at the end, that virtual egress spec will map to a physical egress port where the packet needs to be sent out. All right, there are some conflict resolution activities that need to happen as a consequence of being able to compose these virtual devices together. You may not have written your virtual device thinking about what the forwarding model was and how that plays with other virtual devices that you're now composing together. I'm going to kind of skip a detailed discussion of this, but suffice it to say, we have provided facilities for the slice manager to specify how potential conflicts to the egress ought to be resolved. A lot of possibilities, we believe, by having Hyper4 as a data plane hypervisor and the controller to interface with it as a control plane hypervisor. Possibilities like migrating functions around the network at will, cloning them. If you maintain the rule set separately from the functions, then you can have separate rule sets that you can attach as necessary to whatever compatible virtual devices on whatever physical devices where you might want them to be. and some more radical ones as well. Okay, yeah, there are some cleanup activities at the end of Hyper4.p4. Virtual networking we talked about. There's a facility for egress filtering to avoid broadcast storms. We can handle checksums, and there's some resizing of the parse representation, which might need to be done. And finally, that single metadata field that consolidates all of the parse representation fields has to be written back to that actual parse representation so it can be transmitted. All right, I'm going to skip the code generation discussion. Suffice it to say, there's a lot of boilerplate tables in Hyper4 because you can only have one reference per table in a P4 program, according to commonly available P4 compilers, and the targets apply that restriction as well. So to get around that, we have a lot of redundant tables that differ only in name, and to make the writing of Hyper4 simpler, we basically have a code template approach whereby we can spit out all of the tables and control functions and so forth necessary to be able to handle whatever number of stages and whatever number of primitives per stage we need to be able to handle. All right, there are some performance concerns, but we think there are ways to address these, and in fact we have some very promising approaches that we're going to apply shortly to Hyper4.p4 that we think can take care of a lot of the concerns that we had with our Conext paper from last year. But in any case, we don't think that performance concerns should get in the way of exploring high-level abstractions that are made possible by virtualized programmable data planes. All right, so how are we doing for time? Do we have time for a little bit of demo?
Yes, go ahead.
Okay, let's see what kind of trouble we can get up to here. All right, how does that window look? Can you see what's going on there? Is the font big enough?
Yes.
Okay, so we can kick off a mininet simulation. This mininet simulation will consist of a switch with several hosts attached to it. Some Hyper4 rules have been inserted that are basically your just core functionality for Hyper4 to do anything, but there is no network function that's been defined here yet. So Hyper4 is essentially lifeless right now. It can't really do anything. You can see we've got a very simple topology set up, but if I want to, for example, ping from one device to another, it's not going to work. All right, but I'm going to start up my controller, which is just going to be listening on a particular port. I'll connect to the controller through a client, and once I've done that, I can define some devices and slices. So I'll call this device alpha. I know it's living at port 22.222 as far as the control plane goes for accepting API commands. We'll define it as to the particular type of device that it is so that we can make conversions as necessary. Okay, the packet replication engine needs to be defined. We'll say that it can support 1,000 table entries, and then we'll have a space-separated list of physical ports. Okay. Then we'll create a slice that can get access to this device. And I'll just call it Jupiter because why not? So it exists, but now we need to give it access, so we'll do the grant lease command. We'll specify that we're granting a lease to Jupiter for the device alpha, and we'll say, hey, you can have all 1,000 entries available. Chain indicates the type of lease that it is, so that's the sort of composition abstractions that are possible. So we have virtual device chains made possible. And we'll just give it all of the physical ports as well. All right, now we're going to connect to that. Now we're going to imagine that we are the slice manager for the Jupyter slice. Now we actually need to define some functionality. Okay, so we're going to create a virtual device, and I'm just supplying the path to that virtual device right now. And I'm going to give it a name. So this is going to be a layer 2 switch. All right, so that has been created. So it took that P4 code that was sitting there at that particular path, and it created the virtual device called alpha_L2. So that's our layer 2 switch. Okay, the next thing, we actually need to insert this switch into the device's service chain. So we're going to insert into the physical device alpha this virtual device alpha_L2. The next parameter is the position where we need to insert it. And then finally, we talked about how egress conflicts need to be resolved. So that's the eTrue parameter here. It just basically says always write to the egress spec. As long as the underlying network function, the P4 function, did that. All right, so that generated a bunch of activity that populated some more tables within Hyper4, and now alpha L2 is living within Hyper4. But things still don't work because we haven't written the forwarding rules for it. Okay? So what I'm going to do now is I'm going to configure the egress for this particular lease with a specific egress specification that translates to a broadcast. So this is going to be a multicast setup, and it's going to be filtered so that we can filter out traffic that came in a particular port from going back out that same port, so we can avoid broadcast storms. All right, and then I have a lot of entries defined in a separate file, which I could show you right here. So these are the entries as I would write them for the P4 function, the layer 2 switch P4 function. Okay, so I'm going to issue a command that's going to take all of these rules and interpret each of them for use within Hyper4. So I'm going to interpret a file, and this operation is intended for this particular virtual device. I'm going to specify the style of API, and then here's the path to those entries. So it interpreted those rules and populated our instance of Hyper4 with them. Now we can see the packets actually flow, so that's pretty cool. All right, I would love to give a more complicated example, but time doesn't permit. But we could do things like add a layer 3 router function and take a look at how that interacts with the layer 2 function in order to support forwarding packets on IP addresses where currently Hyper4 does not have that capability written into it, but we can add that dynamically on the fly with a bit more commands issued through the controller. So I'll just leave the demo at that for now. And Bappy, I know I've taken up a lot of time, and I'll turn it back over to you for any questions.
I think we have a couple of questions here. You sort of mentioned performance up front. But, have you been able to sort of run it on, say, Netronome's hardware, or is that something to be done in the future?
That's something to be done in the future. We have not done that yet. We've taken kind of an initial look, but all of my time has basically been spent just working out the concept using BMV2 simple switch on the P4 consortium's repository.
Do you see any obstacles to porting to hardware, or you see it as a matter of compiling?
There may be. So the concerns that I have when I think about deploying this on any particular hardware, are there restrictions on the number of tables that can be defined, the total number of actions that can be defined? I mean, there are going to be hundreds of these for Hyper-4 in order to provide that arbitrary functionality at arbitrary points in the pipeline. So if there are those kinds of restrictions, then the type of configuration that you can deploy to that device is going to be limited. We have written the tool to configure Hyper-4 according to your local limitations, but we have not taken a look and seen what is possible on those Agilio cards.
But sounds good. And if people wanted to use Hyper-4, how do they go about it?
So right now, the controller, we're not releasing that quite yet. We have a little bit more work to do. But if you want to take a look at the Hyper-4 P4 program and even see some demos that we put together for last year's Conex paper, I would urge you to go look at the paper in Conex 2016. The title starts with Hyper-4, and it provides you the Git repository where you can get access to all of the source code, and you can see the specific Git commit that should work for all of the demonstrations. In the future, we plan to deploy some ready-made profiles on Emulab where the whole environment will be set up, and it'll be a lot easier. We have not done that yet, though.
Okay. And I think we're about out of time. Carly, thank you. David, Carly, back to you.
Hi, Bobby. We actually had another question. It was, how does a P4 program compare with compiled C in their ability to scale to high traffic volumes?
That's a good question, and that obviously is very implementation specific, so it's really hard for me to really respond to that. But I would say a lot of people have done a lot of work in getting P4 to be very fast. The whole way that the P4 language was designed was with speed in mind, and that's one of the reasons why they do not allow things like referring to a table multiple times throughout the ingress pipeline, because they have in mind this hardware architecture that's strictly pipelined. Packets just flow from one table to the next. You cannot go back. For reasons of that would introduce bottlenecks in the pipe. I mean, well, not bottlenecks, but that would introduce stalls in the pipeline, as well as possibly be insurmountable from a wiring perspective from one of the engineers that I talked to. So whatever P4 programs you do write, I expect them to be very fast, just depending on what P4 device you deploy them to.
All right. Well, if there are no other questions, then thank you, Bobby and David. And this webinar will be made available shortly on the classroom page on the Open-NFP.org website. And thank you all for attending.
Thank you.